to Physical Science 20 in the AM, period 1. Talking about light today, and it moves in waves, as I was saying. It has properties of wave particles called photons, and you'll see particle properties and wave properties. Now, light is frequency of electromagnetic waves that stimulate the retina of the eye. That's what we call, like, that's visible light. But it's so much more than that. You know how there's sounds that we can't hear, like dogs can hear stuff that we can't? Well, there's what we call light, loosely, common. There's light we can't see. It's really light, visible light, which you guys call light. It's just a small portion of this electromagnetic spectrum. Now, first of all, the speed of light is incredibly fast. Use the letter C to represent, I was going to say the variable, but it's not a variable because C is just always 3 times 10 to the 8. It's actually more accurate, 2.99 something or other, but it rounds to 3 times 10 to the 8, 3.00 meters per second. Now, think about that. That's 300,000 kilometers in 1 second. So it's really fast. Yet over great distances, it takes a long time. It's in the ballpark of 7 minutes for the light we get from the sun to reach the Earth. So somehow somebody flicked the light switch and turned out the sun. We wouldn't know about that until 7 minutes later. And you hear about in outer space, incredible distances are not done in kilometers, they're done in, you guys know, light years. Now, that's a time period. Well, that's because there's such great distances. We talk about something that is 15 light years away, meaning it's so far away, it takes the light that we see in that star 15 years to reach the Earth. Something like that, right? That's a long distance. Anyway, how about that? So here on this panel, okay. So visible light is a very, like this portion of the spectrum is very tiny. Right? It's this section right about now. Have you ever heard of UV radiation? Ultraviolet? Well, okay. First of all, red, orange, RGB, if you guys know what I'm talking about, colors of the rainbow. Well, violet. Beyond violet, ultraviolet rays. You've heard about those. What do you know about ultraviolet rays? The tan. What's the danger? Yeah, skin cancer. UV radiation is more energetic and might cause. The thing is, though, it's a slow reaction, so people don't worry about it so much. But like 40, 50 years later, if you do excessive tanning, it depends on your genetics too, and exposure. You might have melanoma develop or something that could turn cancer, stuff like that. Right? Okay, we've heard a lot. The red area of the spectrum, infrared IR radiation. You've heard of that, right? What do you know about infrared? You knew something about ultraviolet. You guys have heard of infrared. Think about this: an old school stove top, you know, with the where you're going into that. Old school stove top with the, you know, the cinnamon bun burner. Talking about what? Yes, kind of a burner, right? Coil. Okay, it's kind of blackish, grayish, right? But when you heat it up, what color does it turn? Red. Okay. Red, that means that's kind of, it's just outside of the red area of the spectrum. Infrared, beyond red in a sense, or below red or whatever, is heat. Before those radiators at the back, for example, were put over covers, you know that how those work, right? Those old school radiators. You can feel that heat, right? You can't see it though. Did you ever hear of infrared goggles? Hey, Sheldon, you're nodding your head. What about infrared goggles? Yeah, it does. It's some kind of lens that filters it and gives you an image for the red infrared stuff. You can see heat emanating from a body and stuff like this in complete blackness. And visible light passes through a window. But as you know, an oven usually has a glass window, right? And it doesn't pass through glass very easily, right? It doesn't. It'll block it. So visible light passes through windows, infrared doesn't. It has slightly different properties. Okay. Moving away, I was kind of starting in the center, but visible light. Put this way, infrared. You've heard of microwaves. That's literally the band of electromagnetic radiation that you use to cook stuff, warm up stuff, whatever, in the microwave. And those have wavelengths of around 12 centimeters. Then, radio waves, well, that's a big question. Stuff like this. And you notice that these are given both with wavelengths and corresponding frequencies. You can switch back and forth because they all travel at the speed of light. So it's using that V equals F lambda. So nothing new there. These are all widths. Trying to get the idea. Big wavelengths. Tiny wavelengths there. Ultraviolet. You know about X-rays. Stuff like this. It'll penetrate the skin easy, but it won't through bones. You get an image of your bones and stuff. That's what you hear about. You hear about gamma rays. Maybe you do, maybe you don't. You probably hear more about science fiction kind of gamma ray destroyer guns. Very high energy. So, we say light, usually commonly meaning visible light, colors of the rainbow. But beyond that, all of this other stuff is the same phenomenon you just can't see, right? Okay? So, it's really better called electromagnetic radiation, but I still say light. Everything. It travels at the speed. Now, what is light? We're going to just take a look at a video here. Click on it. We'll hear from Grammarly first. Upbeat music, it says. Okay, it must be, why is my, oh, I know why. Here we go.
Light is a strange thing. It isn't just what we can see. Light can be broken up into different types, and we call the whole family the electromagnetic spectrum. So even when it's dark, light is still all around us. Light can be created by making an electron oscillate. This creates an oscillating magnetic field and an oscillating electric field, which we call an electromagnetic wave or light. We often represent light as a wave. Just like water waves, light has a wavelength, a frequency, and a speed. The different colors of optical light have different wavelengths, and so does the rest of the electromagnetic spectrum. Gamma rays are the most energetic, whereas radio waves have the least energy. Even so, light is the fastest thing in the universe. In a vacuum, all light waves, even radio waves, travel at an incredible speed of 300 million meters per second. The Royal Observatory is overrun with squirrels. They're hard to miss during the day because they reflect visible light from the sun, but at night it's more difficult. However, they do emit infrared light, and if our eyes could detect it, we would be able to see them in the dark. If we pass high-energy X-rays through them, the squirrels look very different. Humankind has invented lots of different instruments to show us what our eyes can't see, like our Great Equatorial Telescope, which captures huge amounts of light and allows us to see objects that are tens of millions of trillions of kilometers away. We can see matter interact with light and change it. The gases in the Earth's atmosphere scatter blue wavelengths of sunlight, giving us blue skies during the day and red skies at sunrise and sunset. We can watch sunlight reflect off planets and the moon. During a lunar eclipse, red sunlight changes direction as it passes through the Earth's atmosphere and reaches the moon. And although visible light from stars can be absorbed by dust in space, we can detect the infrared light, which gets through to see baby stars hiding in nebulae. Light can even appear to stretch out. Since our universe is expanding and galaxies are moving away from each other, the light they emit is stretched to longer wavelengths. We call this redshift. Some galaxies are so far away that their light has shifted and stretched from visible to infrared, so we can no longer see them. Stranger still, the universe has unknown amounts of dark matter and bizarre black holes. So even if we can detect all the different types of light, there are still some things in the universe that will remain invisible to us.
Okay. How do you figure out what light is? Well,
Just because I worked in the same field for 10 years.
basically that goes over what we just looked at a little bit. But calculation questions. As I said, there's no new formulas here. I didn't put the formula down. Don't necessarily have to remember it, but we use it all. E equals F lambda. Okay, but I gave a wavelength in this. 556 nanometers. I'm telling you what a nano is. It's a billion. That's pretty small. Right? Because you know that millimeter is pretty small because you can visually see it. And a micrometer is there's 1,000 micrometers inside 1 millimeter. Hard to imagine. Well, inside 1 micrometer, there's 1,000 nanometers. A million of a meter. You know what meters are. It's hard to imagine things that complex. Anything tinier than a millimeter is hard to visualize. However, but we need to change this to meters to use the formula because our speed of light is in meters per second. So this is why I get this. If our wavelength is 556 nanometers. Let's start with it. I'm going to just replace the letter N, that's what nano means, with a million. It isn't in proper scientific notation, but you calculate it. 5, 5, 6, up, 56. Instead of an N, I'm going to put times 10 to the minus 9. You guys follow what I'm doing? I'm just doing a side, just so you get used to what I'm talking. Erase it, so you don't have to erase this. If I say something as 3 kilometers, we know K, kilo, kilogram, kilometer, and stuff like this. Use 1,000, right? Using this method, I'd say, well, 3 tenths. That's the same measurement, right? That's all I'm doing is replacing. Now, this isn't that many zeros, so I actually probably write it up. 10 to the minus 9, though, what does that mean? No. Yeah. 0, 3, 9, 0. Yeah, that's 1, 1, 2, 1. So I'm going to write this out now. I'm going to erase. Something like kilometers is easy to just add the zeros. This is why we're using times 10. This 5, 5, 6, minus 9. I'm going to take this 5, 5, 6. Divide by a million. I could put it in my calculator, but divided by 10 just moves the decimal. Divided by 100 moves it twice. This moves it 9 times. 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, I could take away the curly thing at the bottom. Set right at that one. I thought it was. Okay, there. You don't really want to list your numbers. Like, this is why we're using scientific. Proper scientific notation, by the way, would be 5.56. But like I said, you're calculating. So I'm going to get rid of that. That's your first step. Get things into meters. Okay. Now what? We want the frequency. Well, we know the formula. Now we know the length, right? The weight. We know the speed of light, but we're not told it's any different. We're going to use c. That's 3 times 10 to the 8. We're going to do a little bit of that. Something. What am I getting that for? That's what I'm getting. Speed of light. You'll be told that on the test. By the way, the speed of light in space is 3 times 10. In air, it's actually a little bit slower, but not enough. Like the 3 digits, 3.00 times 10 to the 8 is just 5 meters per second. In water, it's significantly slower. In glass, it's slower, depending on what kind of glass you're using. Plastics, it's so on. In other substances, light travels a little bit slower, but getting ahead of myself. Right now, I'm going to substitute speed of light. 3.00 10 to the 8 meters per second. We're looking for the important. This in meters, this in meters. That means mathematically what I have to do is divide, right? When I divide, the meters will come out. We'll have per second, and that's great because that's hertz, right? Anyway, double less science of fusion. I'm just making some mistakes. You might have to move. So mathematically, I'm going to just left, right, reverse this and put the calculation. Different colors. Now, meters per second. Notice I'm big on units. If you're missing units from your answers, it'll be a penalty. Right? Have to do it. Okay. I'm going to get you guys to use your calculator, not your phone. EXP button, possibly, you familiar with this, right? Or different brands of calculators. TI calculators use the EE button. And so I'll get up much. Maybe it'll look there. So I'm going to go 3. I don't really need the 0.00, but the second function EE for EXP for a lot of yours. Please, that means 3 times 10 to the 8. Divided by 556. 6 second function E. And I'm going to use a negative sign, not a minus sign. Okay. My frequency. Yeah. I want you to do this on your calculator and make sure you know how to do this. 5, 3, 9, 5, 6. Okay, that's way too many. I want to put 3 of them. Pop around. 5.395. I only want 3 of these. That 5 tells me to boost the 9 out. That 9, so that goes to the next 40, right? 40. Times 10 to the 14. And then seconds minus 1 or hertz. I'm going to put hertz down because that's easy. But I could use s to the minus 1 or per second. Same thing. Now, I'm not going to get into this because this particular question, but that's a lot of hertz. 10 to the 14th. A million is 10 to the 6. A billion is 10 to the 9. Trillion is 10 to the 12. That's 540 trillion hertz. Then we have things like, well, yes? The calculator thing? Yes, because this is what I want you all to try it out on your calculator. I'm just going to mention, though, that because hertz is often so large, kilohertz, megahertz, gigahertz, you've heard of these things, right? Okay, back to how I did this. Calculator. I put 3.00 for this, 3.00 on a TI calculator is an EE button. So on your calculator, it might be an EXP button. Do not use the second function log one. But some people have a times 10 to the percent. You put 8. The 10 is built into the EXP button. So don't put a second 10. So you're going to say 3.00 EXP 8 divide by 556 EXP negative 9. Make sure you're getting something. Yes. Yeah, that's what I'm doing. I'm going to pause the video right now and help people out because this is what I want. Okay, we figured out some calculators. Read. How far does light travel in a nanosecond? Now, you did nano before? Yeah, I did nanometer. Well, nanosecond means the same thing. So nanosecond. That's a billionth of a second. That's a. You seem distracted back there. Just phone up. Put that down. I don't care who's in. Okay. How far in meters? Wait. This is our time. But once again, this time, we need to just get it to seconds. So our time is 1 times 10, 1 nanosecond. We're going to replace that with 1 and instead nano. That's what we're going to use. But we want to far, how far? So this is the frequency and wavelength question. We want this is V equals D over T, right? Now, if you're good with this formula here, like I can list it as V equals D over T. I put the numbers in an isolation with D. But if you know this formula good enough, and you can, I think you guys are familiar with this enough, if you multiply up to T equals 2 times D or D times D, you can do it either way, but I'm going to go like this. Oh, we want D. D velocity times. I'm going to put in our 3 times 10 to the 8. Our time we have in seconds. Then we're going to enter this on our calculator. My calculator. 3. Times 1. Negative. Now, I'm going to actually go, this is supposedly measured 3 significant digits, so let me put this to the same time. Okay. Now, with that, so sometimes we can use the V equals D over T formula. just like we did with waves. So it's really re-emphasizing, it's not a new unit, actually, it's the same unit, waves. Yes. Oh, yes. I thought I put down the zeros. Did they, I don't know. Somehow I've got red disappearing ink or something like that. Yeah. And I think I had meters there, but anyways, yeah. We'll see if it stays for another 5 seconds. I don't know what. Okay. Now, something else. How did we figure out what light is? Because, oh, let's see. It's kind of a mystery. We'll make a video in an instant. Oh, I won't.
This episode is supported by CuriosityStream. If light is on and no one's around to see it, is anything actually lit up? The ancient Greeks didn't think so. They
I'm going to pause the
rays
recording.
shot out and return to the eye. That's not how it works. Unless your name's Cyclops. It took over.
I'm going to take a quick look at these practice problems. Let me just mention some things here to get you started on. What frequency is yellow light? Well, this is going to use 3 times 10 to the 8th speed. This is going to use V equals L lambda. We want the frequency, we have the lambda, and we know the speed of light is 2 times 10. We did this one, so you don't have to do it. Modern lasers, femtosecond, 10 to the minus 15 of a second. This is 6 femtoseconds. What is the distance? That's the over to you for your range. And then, how many wavelengths? How many times does 400 nanometers, 400 times 10 to the minus 9, fit into that distance? It's a division. And then 4, the distance to the moon can be found with the help of mirrors, like by astronauts. Also, light is sent to the moon and returns to the Earth in 2.562 seconds. That's the time. Using the defined speed of light, calculate the distance to the moon. If this is done from the Earth, it's a mirror on the moon, comes back, you're going to calculate twice the distance. D equals Q. So then you take your answer and cut it in half. That's the round trip. You've got 3 questions to try. Now, honestly, I think to really bust yourself, you can do it, because there's not much to homework. But I want you to bust yourself in the next 4 or 5 minutes. So I'm asking you,